Okay, let's talk about hard disk drive. The hard disk drive is called secondary storage. Secondary storage is anything that is outside of primary memory. Primary memory, aka DRAM. So the characteristic of secondary device is that it does not permit the direct execution of instructions or data retrieval via machine and load and store instruction. So in case of DRAM, you can use MO, for example, MOV instruction, take a register value. So this register value comes from the DRAM and putting into CPU register. If you can write some value to RAX register, then it goes to DRAM. So we can say CPU can directly manipulate the content of DRAM using this load and store instruction. However, in the storage device, as I told you, it using different specific APIs, like for example, program die or DMA, or for control special instructions or memory map die. It does not allow direct execution of manipulation of content. It's using some specific different I/O instructions. So secondary storage has these biggest difference between primary memory and secondary storage. So secondary storage is usually abstracted as an array of sectors. So each sector typically 512 bytes or 4 kilobytes. All days, these sector size of 512 on modern devices using 4 kilobytes. So what are typical example of secondary storage? Hard disk. The hard disk has this characteristic. The capacity is much large compared to DRAM. Now today the hard disk capacity is like 100 bytes old. Now 2 terabyte, 4 terabyte, much larger than DRAM capacity with lower cost. So it's cheap and large, but it's slow. So to access one block, it takes milliseconds. Comparing to DRAM, where when writing a data to one DRAM, it takes few nanoseconds. Or not few, sorry, 9200 nanosecond takes to DRAM. So comparing these two, hard disk is much slow, but it's much higher capacity with a cheaper cost. And obviously, what makes secondary storage is persistent. Okay, so data survives across power loss, but DRAM is volatile device. Data is gone in case of power surge, power failure. Right, so these are basics. Okay, let's zoom in the hard disk architecture. So hard disk consists of several platters. So platter, if you can kind of internally look at hard disk, there are some kind of big kind of bar center, and some kind of platters are stacked. Okay, and there's ARM. Okay, so this data are placed in this in this track, and there are several tracks consist of one platter. Okay, within the track there are some hard disk manage each sector. So again, the sector can be 512 bytes or 496 byte. Okay, and recall that the disk having a different platter but having a same tracks, we call cylinder. The cylinder group, so we can, if you can say cylinder group, means that it has same track data located in the same track. So later, when we talk about some file FFS file system, which utilize this cylinder group information, so that improving the performance and having a better layout. Okay. So how to retrieve data from the hard disk? There are two parts: mechanical part, electronics part. So to locate, for example, if your data is located in some specific track, then you and hard disk first moving to that track. So this ARM assembly. Then you can place ARM to the specific track. Then disk has to rotate it. Disk usually rotate this direction. We'll put the ARM into specific track and rotate disk to, and put the ARM into track. Then ARM, there is the head. Okay, the head reading data located in some specific sector. Okay, so this location and moving arm is mechanical movement. After that, using this read-write head, put the data into disk buffer. So internally, after that, there's a disk buffer, and the data in the sector are placed in the disk buffer. These are data into DMA out to host to the app. Okay. Okay. So these are, this part, this data path is moving electronics. So which one takes more time? Definitely the mechanical part takes much more time. So these are mechanics, like mechanical movement. So much slower than data path involving electronics, electric data transfer path, this path. Okay. So I would, in a view of device driver, hard disk having this following interface: cylinder, head, sector scheme. So each block. So I want to locate, for example, block 1, or I want to locate block 100. These each blocks are addressed by number of cylinder. As I say, this cylinder, okay, and head, okay, head. So which head and this sector number. Okay. So OS, all this geometry, how many platters exist, how many cylinders exist to one platter, and how many sectors exist in a track. OS operating system knows all this geometry and place data. There's a cylinder head sector scheme. So it's complex, right? So understanding this geometry information is firmer, but this information is hidden to application. This what operating system developers and device driver developers takes this complexity, but these are obviously hassle. So better way to addressing is logical block addressing, LBA. So by LBA is just simply eliminating this information about disk geometry in disk. So disk is simply abstracted as a logical array of blocks. Okay, so like this, there are some blocks. So operating system locate with this block number. Okay, so I want to read block number 2. I want to write block 4 with the content 4. Okay, so these all blocks are associated with logical block address. So the address or block number, same thing. Right? I use it interchangeably. Okay, hardware disk maps this LBA location to actual physical location. For example, this cylinder, which sector, which tracks, which sector mapped into disk. So hardware kind of make life comparable easier for device driver because they perform this mapping. Okay. Again, you may familiar with this kind of concept, right? So operating system building a file and writing data to device, and with this concept of LBA. And then this LBA information, with the internal the disk maps into actual physical location. These inserts are hidden. So what operating system sees this LBA aspect, and these internals are completely implemented in device driver. We talk about this beauty, right? What was it? Level of interaction. Okay, so this level of interaction is implemented by hardware. Okay, so there's a basic interface. So most modern I/O device, hard disk, and later we talk about SSD. SSD also providing this LBA scheme to operating system and device driver. Okay, so to fetching data from the hard disk, it have to consider three important performance factors: seek time, rotational delay, and transport time. So seek time is the moving disk arm to correct cylinder or correct track. Okay, cylinder is group of track, right? So the track. So to locate track, the arm is moving in this seek operation. Okay, depending on the cylinder difference. So if your arm is moving large distance, it takes more time. If your arm moving the one cylinder, it takes less time than this large moving. Yes. And then to locate a sector, the spindle are rotated. So for example, your data is located in 35, then this disk platter speed rotated, so that place this 35 sector into arm head. This delay also, the spinning delay is called rotational delay. Okay, so the speed of this rotational delay depending on the speed of rotation. Typically, desktop hard disk providing this RPM performance speed, and some fast high-end hard disk providing this RPM performance. After that, the data is transferred from the surface, the arm head, into this controller, disk buffer, and send it back to host DRAM. Transport time. Again, these are mechanical movement, these are electric movement, much slower. But comparing these two, seek time and rotational delay, which one takes longer? Seek time is longer, rotational delay. What do you think? So the answer is seek time is much slower. So these are two popular hard disk which having a large capacity, okay? And say this is server and hard disk so providing good RPM, and this is desktop-based hard disk providing much less lower RPM, but seek time is this much. Okay, so clearly hardware enterprise vendors fast, but if you can compare seek time and rotational delay, these are seek time which takes 4 milliseconds, rotation delay on average takes 2 milliseconds. So in case of the desktop hard disk, seek time is 9 milliseconds and rotational delay is 4 milliseconds on average. Okay, so seek time is more than twice expensive than rotational delay. Okay, so these are characteristics. And transport time, yes, these are electronic transport. It's microsecond, uncomparable. Multiple order of magnitude faster than TC or T rotation. Okay, So these are some kind of math to compute performance, but I'm not we are not, let's not focus on how to get it. So these are basic characteristics. So in hard disk, if you can sequentially read a hard disk with maximum throughput, we can get is around 125, and in desktop is 100. So if you are using the old, I'm not sure you still using hard disk based laptop, or if you're copying, the copying speed you may encounter is more than 6. That's normal, right? So reading and writing, so max bandwidth you can use is 120. So when you're copying, so you hit read and write. So bandwidth is separated by 2. So if you can see that 60 copying speed is less than 60 megabyte per second. Okay, that's normal. But that's actually good. So you utilize full bandwidth of hard disk in that case. All right, so there's a performance characteristics of hard. And one thing you have to notice is that, what was the pain of, the hard disk? Seek time, okay? So reducing the seek time is crucial to improving performance. So operating system does not, again, in LBA-based scheme, operating system does not know the geometry. When you are issuing some kind of random IO, your arm is moving a lot for seeking. So which kind of, makes data transfer time much slower because you have many seeks. So if you can issuing the IO request, device internally schedule these block requests to minimizing seek time. Okay, so internal device order disk operation. So because seeks are so expensive. However, this scheduling is called disk scheduling. Is completely different from CPU scheduling. So disk scheduling, CPU scheduling is about how to separate CPU cycle to each thread, but this one is reorder disk request and moving the position of head relative to the required position matters more than length of job. So job length is not. So it is the way of the characteristics of goal for this disk scheduling is to reducing the movement of disk head, so that the seek time to reducing seek time. So there are several disk scheduling algorithms, but let's not talk about different the algorithm itself. You just have to understand that your device can internally manipulate IO operation. So for that one, 2 possible schedulers we can implement or conserving. When your disk request comes, then it goes to disk scheduler and execute. However, there is a non-work conserving scheduler. Non-work conserving scheduler is that sometimes has to wait, even if there is a request comes to device, and it can immediately fetching data from hard disk. But even that, this request can be combined in the future request, so that I can reduce the number of seek time and rotation wait. So this is called some anticipatory disk scheduler, but let's not get bother for the name. So wait, and the system anticipate another request will arrive and combine. Okay. So this, and if scheduler is implemented this way, we can say this is a non-work conserving scheduler. So there are many details about scheduling and how metrics like a CPU, how to measure the performance of disk scheduler and what are characteristics. But hard disk is kind of old device, so we don't need to digging into these details of disk scheduling for undergraduate. If you're interested in, take a look at the textbook, and there are kind of other papers to claiming which disk scheduler performs better, but I think this is not kind of focus on undergraduate. Okay, so there's disk scheduling happening. Here are summary. Okay, hard disk is block type device. and this hard disk using this modern LBA-based interface. Okay, and this disk having a queue, and within the queue, there's some kind of disk scheduler to reducing seek time. All right. So these are kind of some unknown but unrevealed hard some kind of facts about hard disk. Sequential access is much better than random access. Why? Why sequential access is much faster, more than 10x faster than random access? Due to random access causes seek time, many seek time than sequential access. Okay, so again, random access tends to some distant issuing the blocks in the distant LBA, which lead to longer seek time. Okay. And then there's a write amplification. I will revisit this important term. Beware that write amplification. I just briefly kind of define what is write amplification. Given that you are writing 4 kilobyte, okay, so operating system wants to write a 4 kilobyte and measure actual data written to disk with 1 to 4 kilobyte disk and how many bytes. Okay, so no write amplification is that if your operating system write 4 kilobyte and device actually 4 kilobyte. So this bit ratio is kind of equal, then we say that no write is amplified, no amplify. But some device having a more than 4 kilobyte write, for example, SSD, write amplification happen. Okay, so why write it can happen in SSD? Talk about later. Okay, and also an SSD has some characteristics that when writing some same sectors, same LBA locations, disk wears out, meaning that these blocks having a lose the capacity of storing data. But hard disk is much robust for this consecutive writing for same sectors. So in terms of wear down, hard disk is much better. Okay, so these are summary of hard disk. Okay.